Today's lecture introduces us to the concept of traveling waves. This takes our sine waves and cosine waves associated with simple harmonic motion, and now it moves that sine wave or cosine wave along a medium. Okay, so this lecture is primarily about definitions. Okay, there's a whole series of definitions at the beginning, and at the end is going to be the one equation that's going to be really important, and that's the wave equation. It's a fairly simple equation, but you need to keep all the variables and all the definitions straight to make sense of the questions. Okay, and then at the last, there's one slide that basically starts to introduce us to the concept that light is also a wave. Okay, so first off, here's a bunch of definitions. Okay, we've run across equilibrium and amplitude before, as well as frequency in our coverage of simple harmonic motion. So equilibrium is pretty much going to be the same thing as is amplitude. Okay, so in this case we have a wave that's moving from left to right. Okay, the middle of that wave is going to be our equilibrium point, and amplitude again is going to be the maximum displacement from that equilibrium point. Okay, two new words that we're going to use, but pretty common usage, is crest, which is going to correspond to the positive amplitude, the greatest displacement in the positive direction, and trough, which is the negative amplitude point. Wavelength is something new, but we've seen that before. And wavelength is going to be the distance from the one crest to the next crest. It's basically how far has the wave moved in one period, okay, or how in one cycle, how far has that wave moved, okay? And that's going to be wavelength, okay? We can measure it from crest to crest or trough to trough. Okay, we do have to be a little bit careful if I'm measuring from equilibrium to equilibrium, in that I actually need to skip over one equilibrium point. Okay, so that's what that red line there is. Okay, if I want to skip over the one equilibrium point, I can do that. Okay, frequency is measured in hertz. It's basically how many times in 1 second does this wave go up and down. If I stand there in one point and I just count it, okay, 1, 2, 3, okay, and it's 3 times in 1 second, that would be my frequency. Okay, frequency and period is going to be the same that we had for simple harmonic motion. Period is going to be the inverse of frequency, or vice versa. And so period is how long does it take for that wave to go all the way back down and then all the way back up. Okay. Some more definitions. Okay, I've used the term medium, and this is not medium in terms of like small, medium, large. This is medium as in what is the material or what substance is this wave traveling through, and it's the wave energy that travels, not the medium itself. It's not that the string actually moves from one end to the other, or the water moves from one place to another place. Okay, it's the energy of the wave that travels, and that energy moves the medium to represent that wave motion that we talked about. Okay, the wave motion, however, is going to be the motion of the individual particles, the individual string atom or water atom or air atom, okay? And that's going to go simply up and down, or in some cases backwards and forwards, okay? And that's where the two terms transverse wave and longitudinal wave come in. Okay, I have some slides that'll do a little more detail on these, but transverse wave is the wave that we see here. Okay, where the T tells you that it's kind of like perpendicular. Okay, this is the motion of the individual particles of the medium are going to be perpendicular to the direction that the wave travels in. Longitudinal wave, however, the individual particles are going to move parallel to the direction. Okay, so they move along, the wave moves along the direction of the wave itself. Okay, so the last definition we have here is a wave pulse. We'll talk about those briefly. They're not that useful in our analysis, but it helps us to slow things down and look at things one item at a time. Okay, and so a wave pulse is basically just a single non-periodic excitation of a medium. Okay, So this is an example of a transverse wave. It has that sine cosine wave view that we've always been looking at. And the red line there is basically just tracing out that one red dot of the medium. And if you notice, that red dot just goes up and down. It does not go in the direction from left to right. Okay, so the wave medium is going up and down, whereas the energy of the wave goes from left to right. And that's what makes this a transverse wave. Most of our waves, including the electromagnetic light waves that we'll talk about, okay, are going to be transverse waves. Okay, so the vast majority of waves that we'll study are going to be transverse. Okay, this is an example of a longitudinal wave. Okay, again, my wave energy is going from left to right. Okay, and you can kind of see those little dark bands that are traveling from left to right. Those are the wave crests. Okay, and the distance between wave crests is measured by between one dark band and another dark band. Okay, but if I look at one individual particle in this medium, it's only moving back and forth. It's also moving left to right, okay, and back. And so this is an example of a longitudinal wave. And for longitudinal waves, the primary example of a longitudinal wave that we will study are sound waves. Okay, so when you make a sound, okay, as I'm speaking, the sound doesn't, the air particles don't move from my mouth to your ear. Okay, if that was the case, you'd be able to smell me all the time, and that's not the case. Instead, what we have here, okay, is that the energy from my sound, from my voice, moves all the air molecules, and it moves the next air molecule and the next air molecule and the next one until it gets to your ear, and your ear translates those particle motions into sound and into words. Okay. So this is an example of a wave pulse. It's just that little line going back and forth. Okay. In this case, it can have an arbitrary shape. It doesn't have to be a sine wave shape. In this case, it's kind of like triangular. Okay. So this is the most important equation that we'll use in this unit. Okay. And it's the wave equation. So as the energy of the wave travels through the medium, the particles really just move in place. So if I was to measure the velocity of those particles, they have an average velocity of 0 because they don't go anywhere. Okay. However, the velocity of the energy is what I'm measuring in this wave equation. Okay. The velocity of that energy is going to be equal to the wavelength of that wave times its frequency. Okay, so V equals lambda F. Okay, so that's the equation that we're going to be using. The mnemonic that I always used is for the wave equation. Because that lambda symbol kind of looks like a giraffe to me, I always call this visit the friendly giraffe. Some people said it looks more like a llama than a giraffe. So it became visit the friendly llama. I kind of like that because llama and lambda, which is the Greek name for that symbol, are kind of similar. So this slide talks about the derivation of that wave equation. Okay, the wavelength, by definition, okay, the wavelength is the distance that the wave travels in one period. So then your velocity is going to be nothing more than the wavelength time divided, which is distance, times divided by the time that it takes. And since period was the time, it becomes lambda over t. But remember, period and frequency are inverses of each other, so F is equal to 1 over t. So that's how I end up with the wave equation, okay? It's based completely off of the definitions that we've been working with. Okay, this is the last slide we have, okay? Because light is also a wave. Okay, it's an electromagnetic wave, so it has aspects of it that have electric field, and there are aspects of it that are magnetic field, and we treat it as an electromagnetic wave. For the most part, we will focus on its wave property. Yes, it also has particle-like properties. For those of you who are aware that light travels in little packets called photons, We won't be looking at that aspect right now. Light's a little bit more complicated than that. So we're just going to focus on its wave properties. Okay, for now, the speed of light in a vacuum is a physical speed limit. It's this number 3 times 10 to the 8th meters per second. There is nothing that we know in the universe, okay, and until we find something and break Einstein's rules, this 3 times 10 to the 8th is this universal speed limit that we can't exceed. Okay, but all light, as long as it's in a vacuum, will travel at that speed of 3 times 10 to the 8th. Okay, that 3 times 10 to the 8th, however, is only in a vacuum. If I'm looking at the speed of light in water or through a chunk of glass, it's going to be slightly different. Okay, so if that's the speed for light, my wave equation for light no longer is visit the friendly llama. It now becomes see the friendly llama. Or from letter standpoint, C is equal to F frequency times lambda wavelength. Okay, so the speed of light is equal to the frequency of the light times the wavelength of that light. Okay, thank you very much.